The focus is the exact underground rupture point where the earthquake begins. The epicenter is the location directly above it on the surface, where shaking is usually most intense. An earthquake begins at the focus. Seismic waves radiate outward through the earth. They strike the surface at the epicenter. This causes the shaking we feel.
Magnitude measures the energy released at the source. Intensity varies, showing severe damage near the epicenter, but only mild shaking at a distance. The Richter scale is logarithmic. Magnitude 5.0 earthquake doesn't just shake a little more, the shaking, and releases 32 times more destructive energy than a 4.0.
Unlike magnitude, the Mercalli scale is subjective. It classifies an earthquake from I to the I-team. This is based purely on human perception and observed physical damage.
At intensity 5, dishes break. But at intensity 10, expect building collapse.
Primary waves, or P waves, are the fastest seismic waves and the first to arrive. They travel through the earth like a sound wave, violently pushing and pulling the rock. Secondary waves arrive next. Unlike P waves, they whip the ground violently up and down or side to side, creating massive shear forces that tear building foundations apart. Surface waves cause the most damage during an earthquake. They create a rolling motion. They propagate through the shallow layers. This results in maximum structural damage. Earthquakes don't kill people, collapsing buildings do. When the ground violently accelerates, a massive upper weight lags behind due to inertia, bending and snapping the columns. Earthquakes happen when tectonic plates collide, pull apart, or grind together. This immense friction builds deep underground until the rock violently shatters.
Convergent boundaries occur where plates collide. Divergent boundaries happen where plates pull apart. Transform boundaries occur where plates slide past. The Earth's crust isn't one solid shell. It's broken into massive, rigid tectonic plates that continuously surf on top.
The rigid lithosphere floats on the layer below. This is the semi-fluid asthenosphere. Here, convection currents drive plate movement.
Faults are massive, deep fractures in the Earth's crust. When immense tectonic pressure forces these rock masses to grind past each other, the resulting slip creates an earthquake.
This animation shows how rock plates move. The hanging wall slides against the footwall. This friction zone is where stress builds up. Its sudden release causes an earthquake.
India is divided into 4 seismic zones. Zone 5 is the most active, while Zone 2 has the lowest risk. Understanding these zones helps in building safer, more resilient structures.
Based on tectonic activity, India is divided into 4 distinct seismic zones. Zone 2 represents the lowest risk, requiring maximum structural defense. Zone 2 covers areas with the lowest risk of earthquakes. Thanks to stable geological foundations like deep granite bedrock, these regions experience minimal ground acceleration. This zone has low seismic hazard. It stands on stable granite. The seismic factor is weak. Integrity remains intact.
Zone 3 represents a moderate seismic risk. During an earthquake, these areas experience significant ground shaking. This can cause noticeable damage to walls and facades. Zone 4 presents a high seismic hazard, ground acceleration. Buildings here face massive lateral forces, detailing, absolutely mandatory to absorb collapsing.
Zone 4 presents a high seismic hazard with severe ground acceleration. Buildings here face massive lateral forces, like ductility is mandatory. This absorbs the shock without collapsing.
Zone 5 is the most dangerous seismic zone, facing catastrophic earthquake risks. Here, extreme ground acceleration can literally turn solid soil into liquid mud. The reason Zone 5 is so dangerous is the ongoing collision between 2 tectonic plates. The Indian plate is relentlessly ramming into Eurasia. To survive extreme earthquakes, engineers completely decouple the building from the ground using base isolation. Massive rubber and steel isolation decouples a building from the ground. Heavy bearings absorb violent ground acceleration. They flex to absorb the shock. This keeps the superstructure steady. To prevent ultra-tall skyscrapers from snapping during an earthquake, engineers install a massive, heavy pendulum near the roof. When the building violently sways one way,
this is a massive tuned mass damper. It sways to counteract building movement. Giant hydraulic dampers absorb the energy. This keeps skyscrapers steady.
When an earthquake forcefully accelerates the ground, this inertia creates a violent whiplash effect, putting immense, destructive shear stress directly on the base columns. Buildings must support vertical gravity loads.
But lateral loads, like wind and earthquakes, are the real horizontal threat. This pushes structures to their drift limit, causing dangerous base shear concentration. When the ground accelerates, inertia causes the heavy mass to lag behind. This creates a violent whiplash effect, concentrating extreme stress at the base.
When a severe earthquake hits, normal columns can bend like rubber, causing a building to sway dangerously. To stop this sideways motion, engineers build sheer concrete
To resist
spine.
powerful horizontal forces like earthquakes, buildings rely on a massive concrete shear wall. This acts as a rigid structural spine, keeping the entire skeleton safe and
Standard
stable.
frames easily fold. Engineers use cross-bracing. Squares become rigid triangles. Braces absorb tension and compression. Geometry stops the sway. To survive extreme earthquakes, buildings use massive shock absorbers just like cars do. Engineers install heavy-duty friction dampers deep into a frame can break.
Friction dampers act like shock absorbers. During quakes, these plates slide. This converts kinetic energy to heat. This keeps the building safe. They are highly effective.
Concrete is incredibly strong, but during an earthquake, it becomes dangerously brittle and can snap like a twig. To prevent total collapse, engineers use ductile detailing. If buildings are built too close together, earthquakes turn them into deadly battering rams. Because buildings of different heights sway at completely, they move out of sync during a tremor.
This is seismic pounding, when buildings collide. Different heights cause them to sway at different speeds. Without a proper gap, they destroy each other.
Retaining walls need total seismic defense. During earthquakes, earth pressure increases dramatically. A deep shear key anchor prevents sliding, while porous gravel backfill dissipates water. They ensure structural stability.